Hi, my name is Fredrik Gustafsson. I'm professor in sensor informatics at the Department of Electrical Engineering at Linköping University. Among other things, I have developed this course in sensor fusion, from which we will get some modules to your course, TNK106. And the purpose of this introduction is to introduce some concepts important for your project on search and rescue. So what I will talk about is more thoroughly covered in the coursebook Statistical Sensor Fusion, published by Student Literature. We also have a MATLAB toolbox with a manual and an app for Android called the Sensor Fusion app. It's available in Google Play, and from that you can collect and stream sensor data from your sensors on your cell phone into MATLAB for some real-time applications. And there is also a template for a real-time filter available on the course homepage. But I will talk today about the basic concepts in sensor fusion, the sensor models, motion models, Kalman filters, and a couple of search and rescue related examples. But the goal in sensor fusion is typically to localize a device, a user, or an object in a sensor network. So there are a few fundamentally different sensor models available in sensor networks. They all apply to radio measurements, but also to acoustic, sonar, and seismic signals. And they are of four different types. We have time of arrival that gives a direct measurement of the distance between the object and our sensor. We have time difference of arrival applying in sensor networks where the receivers are not synchronized with the transmitter, and that means that we have an unknown offset that is added to the range for all sensors. That corresponds to the time offset. So in our GPS receivers, for instance, we have an unknown clock bias in our own clock while the satellites are synchronized. So that is basically a time difference of arrival problem. Direction of arrival, then we measure the angle between the transmitter and receiver. And RSS, which is the most typical sensor in search and rescue project, that can be phrased as that we have the range between the transmitter, x, the position we are looking for, and our own position, pk here. But we don't observe the range directly like we do in the time of arrival here, but we take the logarithm of the distance multiplied by the so-called path loss constant. And then we have an unknown transmission power. So the transmission power is attenuated by terrain and distance in this way. So we can note that they are all of the same kind. We can express what we measure as a function of the position of the transmitter using some nonlinear transformation, h of k here. The time of arrival, as I said, measures range between transmitter and receiver, while RSS is a nonlinear transformation of range. So a general problem formulation is to minimize a cost function in the unknown position x, where we have available measurements, and there are a few different types of loss functions. The most common one is nonlinear least squares, where we look at the deviations between what we observe and what the model says about the sensor observation for a given x. And then we square that and sum over all observations. That's the norm square notation here. There's a weighted variant as well, where we weigh the sum of squares with the inverse covariance matrix, and that takes care of that some measurements might be better than other ones, so that they will get larger weight by this weighting here. And if we happen to know the noise distribution of the measurement noise in the sensor, then we can optimize the likelihood function instead. So PE here is the distribution of the measurement noise, that is the deviation of y and the model. We can look at one example here, how the loss function looks like in a sensor network. So we have 4 receivers here, the black and green dots. We have an unknown object located here. First, we assume that we measure the range between each receiver and the transmitter here. The loss function will then have level curves according to this contour plot. And we can see that locally around the true object position, the level curves are more or less elliptical. And that means in optimization that it's quite simple to find the minimum point by iterative search algorithms. A bit more interesting is the DPS example here, where we have time difference of arrival measurements, because in this case the level curves of the loss function are much more asymmetric, and that might imply that it's a bit harder to numerically find the optimum here by iterative search. So the first example here. So what we did in this master thesis project is to develop a solution to the nonlinear least squares problem for a stationary object. So here we have hidden a cell phone put in hotspot mode out in the field here. And we have a drone with an operator, where the drone is equipped with a cell phone that reports RSS values to the operator. So the pilot is looking at this image here, so he can see where he has done the data collection, and he can see what the current estimate of the target position is given the RSS measurements so far. So that means that the pilot can make an educated guess of where is the best path to fly to get the most out of the measurements. So here he decided to make a turn at this part here and going back again. So let's look at the video here. So we start here in the grass. The drone is lifted by the operator, and we have many measurements on this point here before we start to fly. Let's wait a few more samples. So here we get more samples. We still don't know where the target is. We guess that it is close to our positions here, but once we get the larger baseline between the measurements, the estimated position moves away quickly. It moves a lot here in the beginning before we get sufficient information to get an accurate estimate. But here we can see that the estimates starts to converge. We can see the true position here, but it's not available to the pilot. He's just flying on intuition here and using the red graph. And here he decides that, okay, I think I've got enough information, so let's fly home to home base and send out the rescue patrol to look around this position here. So that this example shows how a drone can assist a search team in finding a good initial position for where to look for the victim. So this example applied to a stationary object hidden in the terrain. But what happens if the victim is moving around? Then we need a motion model for modeling how the victim moves. And the simplest and most typical motion model in Kalman filter literature is to use Newton's force law, F is equal to m times acceleration, which corresponds to what is called the nearly constant velocity model. And that can be written in any dimension. So in one dimension, that is when you're moving along a road or railroad, for instance. 2 dimensions is what is typically for search and rescue applications, but also 3-dimensional search is possible. In all cases, the motion model can be written in this state space formalism, which has the interpretation that the next position will be the current position times the speed multiplied by the sampling interval. So we get a transition here in meter. And then we have the process noise that corresponds to the deviation from a straight line motion, which happens to be multiplied by the sampling interval squared over 1/2. While the speed at the next position is equal to the speed currently plus the process noise times sampling interval. How you actually can get this state space model from this simple Newton's law is explained in one of the modeling lectures, basically by applying a continuous state space model of this equation and then discretizing it. But this is the standard form of a motion model for the Kalman filter. So it's a linear function of a state plus a linear function of the process noise that gives the next state here. So to get a typical application of the Kalman filter, we can have a position sensor, for instance a GPS, that provides a direct observation of the position plus noise. So the standard deviation here is 3 to 5 meters. And if we add this sensor model to the state space model, the Kalman filter applies directly. So what is the Kalman filter? Well, as I said, it applies to linear state space models of this form. It can actually be time varying as well. We can have a K on F and H here. We need a description of the process noise in terms of a covariance matrix, and the measurement noise has a covariance matrix R here. They are both assumed to be zero mean. So the Kalman filter can be seen as a computer program that recursively updates the estimated position and velocity, that is the state for the example before, after every measurement, that is every GPS position we get. So this is a navigation example, I should say, that we don't know our own position. We need a more accurate estimate of the position than the GPS can provide to us directly. So the Kalman filter equations can be summarized as these 4 recursions. So there's a time update that applies in between every sensor observation, and after each sensor observation we apply a measurement update to update both the estimated state, x hat, and its covariance matrix. And geometrically you can consider the covariance here to be an ellipsoid around the states. So if you want a confidence interval or confidence region around the state, P provides an ellipsoid that can be interpreted as 99% confidence interval for X. Sometimes you don't have a linear state space model, but a non-linear state space model. So the next state is a nonlinear function f of the current state and process noise, while the sensor observation is a nonlinear function of x. So actually all the sensor network measurement models are of this kind. They are not linear in x directly. The GPS model was linear, but not the other ones. And we need the covariance Q and R for the noise. So what we do to transform this model to a Kalman filter model is to apply a first order Taylor expansion to f and h around the current estimate. So we linearize f of x, comma v around the current estimate x hat. The best guess of vk is 0, so we plug in 0 here. And here we get fk as the gradient of f with respect to x, and g is the gradient of f with respect to v here. And the same thing applies to the sensor model here. One example of this from Cold Modern Zoo. One year we put BLE tags on all the goats in the children's farm, and we put 5 cell phones around the fence line for collecting RSS measurements from each goat. So the figures here correspond to cell phone positions. And BLE pings include a MAC address, so we can easily separate the different goats and then run one Kalman filter for each goat. So what we'll see in the movie is the estimate of a few of the goats and how they are updated over time. So let's start the animation. So what happened this day is that we first started cell phone number 2, and that means that we measure RSS just in one dimension. So that means that the estimate can just move radially to that sensor. Then we put on sensor number 4 located here, and then that means that we can also update radially from number 4. And it takes some time to walk around the fence line here to start all phones for data collection. All the analysis was done offline. So we illustrate only the green goat here, and we can see how it moves in this enclosure. We can also note that we don't get a very precise position because RSS measurements are not so precise, and we have a lot of disturbances here. It's a bit hilly terrain and a lot of trees that gives random disturbances to the RSS measurements. But anyway, we get some kind of information of where it is and how it moves over time. So for the project on search and rescue, there are a few design issues. So I have a checklist here. So the checklist includes deciding if the rescue object is assumed to be stationary. Then we can use a very simple state space model where the state is assumed to be constant over time. And in fact, the Kalman filter boils down to nonlinear least squares, but to keep it in the same framework, we can apply the Kalman filter for this special case. If the object is assumed to be moving, then use this simple motion model to start with. Then we need to decide if the sensor is moving or stationary. The sensor can be stationary if you have a scanner at fixed positions. We need to know its position because we need to compute the range between the sensor position and the target position. If it's moving, we can use GPS in the scanner to compute or measure our own position, QK. And this applies if you use the cell phones or the rescue team as as RSS scanners, or if you are using a drone for collecting the RSS measurements. To choose algorithm, if the motion and sensor model are linear, then use the Kalman filter. If they are mildly nonlinear, then the extended Kalman filter works just fine. If they happen to be highly nonlinear, or I should also say here, if the noise is far from being Gaussian, then the particle filter might be advantageous to use. But start with simple things first. That's my general recommendation. That's all. You have a list of lectures for deeper understanding of this subject on the course homepage. Otherwise, I wish you good luck.